Good morning, respected faculty members and fellow students. This project is created by Rahul Chandrasekhar and Aman Singh from Mechanical Branch. This video is presentation for our B.Tech project on design improvements of mechanical prosthetic arm. The project was guided by Professor Bikash Routh. The aim of this project is to investigate 3D printable prosthetic arm designs available on the internet. Study mechanics of arm and hand of a human, calculate all the mathematics of the mechanisms of prosthetic arms of previous designs, finding out the flaws and problems in old designs, creating new improved designs in CAD software, and finally fabricating prototypes using a 3D printer and testing it. Coming to the first chapter of this report, which is the introduction. Let's start with prosthesis. A prosthesis or prosthetic implant is an artificial device used in medicine to replace a missing bodily component that may have been lost due to accident, illness, or a birth defect. Prostheses are designed to replace the missing body part's lost functionality. In underdeveloped nations, there are about 40 million amputees, yet only 5% of them have access to prosthetic limbs. The expense of traditional prostheses, which may vary from $1,500 to $8,000, according to the American Orthotics and Prosthetics Association, is prohibitive for the majority of amputees. Hence, 3D printed prosthetics can be an excellent alternative to conventional prosthetics since they can be purchased for as little as $50. Also, utilizing 3D printing, it is feasible to create prosthetic limbs more quickly. To pay the overhead cost of creating tools in the conventional manufacturing method, large-scale production is necessary. Yet regardless of the number, 3D printing keeps the cost of producing a single item same. Traditional manufacturing processes are costly, precise, and skill-intensive, especially when assembling complicated pieces to create complex mechanical structures. With 3D printing, which can produce an entire complicated component in a single step. So, we decided to work on 3D printed prosthetic arm. The methodology of design started with analysis of previous designs. There are several 3D printed prosthetic arm designs on the market today that use simple mechanisms and are easy to fabricate. But after reviewing all these designs, some modifications can be made to further increase the usefulness of these arms. Here are some commercially available 3D printed arms. All of the mentioned 3D printed prosthetics use strings to control the flexion and extension of the fingers, which are either moved by the wrist or the elbow. However, as all of these models lack independent finger control, they are all limited in their ability to grasp irregular items. We did a literature survey for this. This table is taken from a research paper that contains qualitative analysis of 58 3D printed prosthetic devices. We can see that out of 58, only 14 prosthetics are body-powered, and all body-powered prosthetic have no independent finger movement, also called adaptive grasping. So little modifications are needed to keep this prosthetic basic and enable enhanced hand control for better grasping. We then made simple free body diagrams to calculate the theoretical forces, torques, and other motion in our design. Starting with the fingers. Each finger is divided into two links which will be rotated with the help of a string. Assuming its axis as origin, the torque generated by a string on our design with tension T will be equal to 5 Newton millimeters. Each finger link is capable of rotating 90 degrees and will go back to its original position with the help of an elastic band countering the string. Next to this, we calculated length of string required to contract a finger. For adaptive grasping, we decided to design a pulley mechanism which will distribute tension from one string, which will be pulled from elbow and distributed to 5 strings going to each finger. For the following free body diagram, let's assume tension generated by elbow rotation on string equals Te. In a design with equal distribution of this tension on all fingers, tension in each finger are equal to each other. Applying force balance equations, we found out that pulley system will increase the tension going into each finger by 500% compared to previous designs. After these calculations, we started designing a 3D model of our design in Fusion 360. First, we designed the hand, which included upper finger link, lower finger link, upper palm, lower palm. Their parts can be connected by anyone using M3 nuts and bolts. Following are the images of CAD drawings with dimensioning of the hand. Then we designed the elbow link, which is going to pull the string which is used to initiate the fingers of our design. Following are the images of CAD drawings with dimensioning of the elbow links. At last we designed the CAD model of our pulley mechanism, and here is the CAD drawing with dimensioning. After designing CAD model, we selected appropriate parts and materials for our model. For smooth rotation, we selected bearings of diameter of 6 mm, 10 mm, and 13 mm. For string, we selected Griffin nylon thread of size 12, and for printing, we selected PLA material. The 3D printer used by us is Creality Ender 3 printer. This printer has nozzle speed of 50 mm per second, minimum layer height of 0.1 mm, and its printing technique is fused deposition modeling, or simply FDM. It is an additive manufacturing process that involves the extrusion of materials via a nozzle and the subsequent joining of those layers to produce three-dimensional structures using a 3D printer. For slicing software, we used Creality Print to generate G-code of our models. This software allowed us to add support structures, correct orientation, adjust layer height, infill percentage, and bed temperature. We then checked the simulation of our print through the software before printing. For 3D printing, we had to first calibrate the nozzle position and align the printing bed. Then we started printing all the parts of our design, which took more than 48 hours of printing time with 20% infill. After printing each part, we started assembling our model, starting from finger links towards the elbow joint. After printing the palm, we tested the adaptive grasping to grab various objects as shown in the video. Since we didn't have access to testing rigs for prosthesis arm, we performed static stress simulation on Fusion 360 and applied load from 0 Newton to 250 Newton on the finger links and found out that our model can take more than 150 Newton tension from strings and have a factor of safety higher than 3. Coming to cost analysis of our project. We have spent Rs 749 on PLA filament, 640 on ball bearings, 110 on elastic, 20 on nylon threads, and 60 on M3 nuts and bolts. The total cost came out to be Rs 1579. For results, we calculated the theoretical weight of our design, which came out to be 1,089 grams, which is significantly lighter than an average motor-driven, battery-powered prosthetic arm. Summarizing the conclusion, a prosthetic arm was successfully designed in a CAD software and new mechanism was successfully added. Then all the G-code was created for the prototype, which can be used for further recreation of the design prototype, and it can be improved further for real-life usage. The finished 3D printed prototype was created successfully. However, for a finished product, this design needs more iterations of prototypes for regular usage. Its ergonomics and simplicity of designs can be improved further. Thank you all for listening to this presentation.